All right, so I wanted to make you guys a short video about a couple questions. One was problem 25C, and so here's the problem. Given f of x is 30x cubed minus 31x squared plus 10x minus 1, and you also know that f of a half is 0, f of a third is 0, and f of a fifth is 0. We're supposed to factor f of x using this knowledge. So the way we can do that is to use the factor theorem 3 times. It gives us this factor, and that factor. And so if you put that all together, what we have is that, f of x has got to be something, whatever, just say stuff, times these factors, right? But on the other hand, we know f of x is this. So if you look at it, that means that this stuff has to just be a constant, because if you multiply this out, you've got x times x times x, which gives you x cubed. So all that's left over room for is a constant there. So we can say, okay, there's a constant, let's call it a. But on the other hand, we know when we multiply this stuff out, we get 30x cubed and so forth, right? So if I just focus my attention on the highest order term, a times x times x times x, that's got to give me the 30x cubed. See, I have to have ax cubed is equal to 30x cubed to make those coefficients match. That forces me to put a equal to 30, which then means that we have 30 times this is the factor, there we go, we factored the polynomial. And if you want, you can write 30 as 2 times 3 times 5, and you can multiply it through to get this alternative kind of like pretty form of it, but what's in green is also good. So my apologies, I seem to have solved problem 25C for you. You can hopefully forgive me. So I've got a bunch of examples here to share with you. And I intend to scan these pages and post it as a PDF in Canvas. All right, guys? So if you want to look that up to follow along, you can. So just to talk a little bit about graphing circles, ellipses, and hyperbolas, or identifying. Sometimes we won't graph, we'll just identify. So basically the story here is to help with problem 31. And every one of these examples, what we're going to do is we're going to start with the given equation. Then we can complete the square, all right? But I haven't completed the square yet. First thing I do is isolate the squared term. So I factor out the terms with y. This is a minus on the y squared, I factor a minus out. And then I can complete the square inside that parenthesis like that. So I've got, y minus 3 quantity squared, and then minus 9. And over here, y plus 2 quantity squared minus 2 squared, which is 4. And then rearranging stuff, that gives us x plus 2 squared minus y parentheses y minus 3 squared is equal to apparently minus 5. So that tells me that whenever you got a difference of squares equals to a constant, what you're looking at is a hyperbola, all right? This one, the center of the hyperbola is minus 2, 3, and here's a graph of it. If you want, you can see, if you put y equal to 3, then you've got minus parentheses x plus 2 over 5, minus parentheses x plus 2 squared over 5 like that, right? And that equal to 1 has no real solution, which tells me that the graph doesn't cross y equals to 3, all right? So y equals to 3 is like here. It doesn't cross that. On the other hand, if I put x equal to minus 2 and work through it, I get 3 plus or minus the root 5. That gives me what are called the vertices of the hyperbola. This point here and that point there, as you can see. So anyway, big picture here, if you have a difference of squares, it's a hyperbola. Then the real question then is just, does it open up and down? Like, does it open vertically? Or does it open horizontally? Let's look at a couple more examples. These should all help you. These should help you solve problem 31, all right? They're related to problem 31. So here we have x squared minus 6x plus y squared minus 2y plus 30. So this time I can just complete the square because I've already got x squared and y squared on their lonesome. So x minus 3 squared takes care of these two. If I subtract the square of 3, which is 9, then I have y minus 1 squared, which minus 1, there's completing the square on these two terms here. And that gives me this. But then when I isolate the squares, I get x minus 3 squared plus y minus 1 squared, well, that is equals to minus 20. Well, there's no way you can achieve that. You can't have a sum of squares equal to minus a number. So what that means is that the graph of this equation is no points. It's nothing. The graph of it's nothing. That equation has no solutions. Example 3, again, take my equation, complete the square, isolate the squares. This time, it works out to sum of squares equals to 0. Well, the only way this can be working out is if both of these are separately 0. And the only way that can happen is if x equal to 3 and y equals to 1, so the graph is a single point. Only solution is 3, 1. All right, so these are both kind of very odd, exceptional cases in this game we're playing. Example 4, again, we are given this equation. I complete the square. This time we got fractions because 5 over 2 it's a fraction, so I have to subtract the square of that, which is 25 over 4. And completing the square on y works out nicer. There it is. And then I isolate the variables on one side, and I add the constants to the other, and I get x minus 5/2 squared plus y plus 1 quantity squared is equal to 29 over 4. And, well, that's a circle. What that is a circle with radius square root of 29 over 4, which is square root of 29 over 2. And the center, we can see by inspection, is at 5/2, comma, minus 1. And here's a picture of it. This is what the circle looks like, approximately, all right? So, you know, so there's really three things to, well, yeah, basically three things for you to learn, mostly, which is either it's a circle, an ellipse, or a hyperbola. I guess there's 5 things, though, right? Because the other possibilities, it's nothing or it's just a point. I think that's pretty much it for what we're looking at in terms of these kinds of equations. But, I mean, there's more if you make the equation a little bit more general, but I'll talk about that in class to you guys when I have a minute. Let's see here. So, I mean, this is part of a larger story, what are called conic sections, but let's focus here. So this equation is given. I complete, this time I've got a 9 in front of the x and I got a 2 in front of the y. So the first thing I do is factor out the 9 and factor out the 2 on the x terms and the y terms, respectively. See, 9 times x squared minus 2x, and then over here 2 times y squared plus 4y. Then I can complete the square inside the parentheses, like so and like so. And then I multiply the 9 and the 2 back out. That gives me this minus 9 here, and this 2 times minus 4, which gives me minus 8 here. Then I move them to the other side to the 17. And then I divide the equation by 17, actually. And that gives me this, which then I rewrite one more step like this. So I rewrote it as a sum of the square over a fraction. See, 9 over 17 is the same as 1 over 17 ninths. 2 over 17 is the same as 1 over 17 halves. And so you can compare this pattern with the standard form of the ellipse equation. And from that, you can see that the center is at 1, comma, minus 2, and that the a, if you will use that, that notation, a is equal to the square root of 17 over 9, and b is equal to the square root of 17 over 2. Now, in terms of decimals, that's about 1.37 and about 2.93. And so it's pretty simple. The way to graph the ellipse is you just go to the center and you go plus or minus a in the, let's see here, plus or minus a in the x, I believe, right? In the x direction, plus or minus a, and then plus or minus b in the y direction. So I can get these sort of 4 points on the outside of the ellipse that kind of pretty much tell you what it looks like. See, the center's at 1 minus 2. I add b to get to the top. I subtract b to get to the bottom. I add a to get to the side point. Sorry, it's a little bit out of frame. Let's scooch that over a bit. There we go. So I add a to get over here, 1 plus a. To get that point over there, 1 minus a. All right, so that's about, you know, here's the a and the b numerically. So I don't want to write the ugly numbers over here. I just want to emphasize how you get from the center point, either by adding or subtracting b in the vertical sense, or adding and subtracting a in the horizontal sense. And that's how we get the ellipse, if you want to graph it. But a lot of times we're just after, we're not after a careful graph. We're just after a quick evaluation. Hey, is it a circle? Is it an ellipse? Is it a hyperbola? And you don't need to graph it to figure that out, right? Like this, I can take one look at this and go circle, because it's a sum of squares equals to a number, and both of the squares have the same weight. So I can see, though, that to be more specific, it's a circle centered at -3, 5, and the square root of 25 is 5. That means its radius is 5, and here's a picture of it. So you got your center point, and basically you're going the radius out in any direction from that center point, and that gives you these 4 points. So it's the same idea I just did with the ellipse in terms of adding and subtracting A and adding and subtracting B. It's just in this case, A equals B equals the radius, right? Because a circle is the special case of an ellipse. But there's a graph of the circle. This next one here, 4x squared plus 9y squared equals to 36. I say graph it. So I divide the equation by 36, which gives me x squared over 9 plus y squared over 4 equals to 1. And if we compare that to the ellipse in the format x squared over a squared plus y squared over b squared equal to 1, this is the equation for an ellipse centered at the origin, all right? And you can see a equals to 3 and b equals to 2, because the square root of 9 is 3 and the square root of 4 is 2. And so that gives me this picture. I go plus or minus a in the x, which takes me to 3, 0, and minus 3, 0. And plus or minus b in the y, which takes me up of 0, 2, and down to 0, minus 2. And that's how we can graph an ellipse. You go to the center and you go plus or minus a and plus or minus b, and that gives you the 4 points, and then you can kind of use your imagination to see what the rest of the thing looks like. So an ellipse is a sum of squares. A circle is a sum of squares, but the squares match. And a hyperbola is when there's a difference of squares. Here's another one of those. Example 8. So here we go. X plus 4 squared minus y minus 2 squared equals to 1. Graph it. Okay, so this is a hyperbola. It's centered at -4, 2. All right. And if we look at the case x equals -4, then that makes this term 0, and it leaves us with minus y minus 2 quantity squared equals to 1. But that has no solution. So that means the graph does not cross the x equals -4 line. That means that it must be opening horizontally. All right, and you can figure out where the vertices are by putting y equals to 2. That gives us either x equals -5 or x equals -3. So the vertices are at -5, 2 and -3, 2, which are this point and that point. All right, those are the vertices, the turning points, if you will, of the hyperbola. It kind of looks like a pair of parabolas put together, but that's not quite honest, because like if I did this really carefully, they should really closely approach these asymptotes, but they don't quite get there. So they're, in that sense, they're asymptotes. The equations for the asymptotes you can get from getting rid of the constant on the other side and just setting these terms equal. And when you do that, you either get y equals x plus 6 or y equals x minus x minus 2, which cleans up to give you y equals -x minus 2 or y equals x plus 6. Those are the so-called asymptotes. So if you can find the asymptotes for the hyperbola and you understand that it opens, either horizontally or vertically, then you can pretty much graph it. Especially if you also know the vertices pretty much fix it. If you know asymptotes and the vertice and whether it opens horizontally or vertically, you can pretty much graph this thing, right? All right. So next up, probably another hyperbola. Yep. Here's another one. This one's nice. It's centered at the origin. Sorry, I'm trying to be quiet because my kids are sleeping. Let's see here. So minus x squared plus y squared equals to 1. So we got a hyperbola centered at 0, 0. If you put y equals to 0, you get minus x squared equals to 1, which means there's no solution, right? So if there's no solution at y equal to 0, well, y equal to 0 is the x-axis. So we're saying the graph doesn't cross the x-axis. That means that it's a vertically open hyperbola. All right, so to find the vertices, put x equal to 0. You get y squared equals to 1, which has solutions y is plus or minus 1. So you got vertices at 0, 1 and 0, minus 1 here and here. And so you can also find the asymptotes from setting it equal to 0. This time the asymptotes are just plus or minus x, which are these dotted lines. All right, so, and there's a rough picture of the hyperbola, right? So in summary, there are two kinds of hyperbolas. There's either ones that have plus x squared minus y squared terms. Those ones open horizontally. Or you can have minus x squared plus y squared terms, and those open vertically. In both cases, you can find the equations for the asymptotes by just setting the squared terms equal, which will give you y is equal to y naught plus or minus b over a times x minus x naught. A lot of times, if I'm going to ask students to graph this, I'll just make b over a equal to 1 sometimes. But I'll try to make it something not too complicated, like 1 or 2 maybe. Anyway, you are allowed a formula sheet for the test, right? So these would be smart things to put on the formula sheet, just so you can double check if I ask you a question about a hyperbola, and part of the question is, does it open horizontally or does it open vertically? Well, if you've got this information on your sheet, you're ahead on the game, right? Just saying. Okay. Especially since this material is relatively new before the test, you want to kind of, hedge your bets with the formula sheet, I think. So one last thing, systems of nonlinear equations. You also had a question about this. This is like problem 30. One of you asked me to, look at this problem. So I think I changed the numbers from what's in the homework, but it's pretty similar. Hopefully the homework problem has nicer solutions, but I make no guarantees. But here's the concept. When you're solving two equations in x and y, the simultaneous solutions of both equations correspond to the intersection points of their respective graphs. Now, we already saw this when we solved linear equations. Like if there's a simultaneous solution to both linear equations, the intersection is just 1 point, right? Or it could be that they're the same equation, and then there's infinitely many points of intersection. So we saw that before. But here it's different because now we're dealing with circles and hyperbolas, and they can intersect in exciting new ways. See, if I have this equation and that equation, I can either subtract them or add them, subtract or add, and in so doing, I eliminate one of the other variables. So this time I get, x squared is 23 over 2. Over here I get y squared is 9 halves. Use the square root property, I get plus or minus 23 over 2, or plus or minus root 9 halves. But notice that the plus minus here and the plus minus here are logically disconnected. They're not forcibly linked. So if you think about it, that means there's 4 possibilities. And those four possibilities make sense because there's this point, this point, this point, or that point on this graph. And for reasons I don't understand, failed to put a dot right here. How? Come on, there we go. That's bothering me. Anyway, so 4 solutions corresponds to 4 points of intersection. All right, now one more example and then we'll be done for this short video. Again, sorry I'm late to class. I'm making up for it now. Well, I'm trying to anyway. This would probably be more useful than whatever I would have done if I was on time anyway. Okay, so I assume solving your homework problems is helpful, but solve x squared plus y squared equals 16 and x minus y equals to 2. This is like problem 32 in the mission, okay? So this one, I'm going to use substitution to solve this system. So if I solve this equation for y, I get y equals x minus 2. Then I can just take that and plug it into this y, and that gives me x squared plus x minus 2 squared equal to 16, which we're happy to see that because, hey, that's a quadratic equation. So I multiply it out, I group terms, I divide by 2 to make life easier, then I complete the square, isolate the square, use the square root property, I get solutions 1 plus or minus root 7. Then, since it's also the case that y is equal to x minus 2, I get correspondingly minus 1 plus or minus root 7 when I subtract 2 from these. And so that means that this plus or minus and that plus or minus are linked. They're the same plus or minus, all right? And consequently, we get this point and that point. Those are my solutions, corresponding to the fact that this line intersects the circle at 2 points. And, if you start thinking about this, you can kind of anticipate other things that could happen, right? If I've got the equation of a circle and the equation of the line, what could happen? I could get 2 points, right? If I hit it, so it just kissed that 1 point, just that 1 point, I could have that like tangent line to the circle. I could have just one solution, right? That's another possibility. But what else could happen? You could have the circle. I mean, you could have the line like out here, right? If the line was out here, then you get no solutions. So for a line compared with a circle, you're probably either going to get no solutions, one solution, right? Or two solutions. And I think that's pretty much what can happen. So anyway, just saying, if I give you one of these problems, that's kind of what to look for. It's one of those three cases, right? And in contrast, if you want to think about that kind of game over here, what are the possibilities? Well, if you've got a hyperbola and a circle, it seems like it could be that you get just two solutions if it just so happened that one branch cut through the circle but the other didn't. So you might get two solutions, you might get four solutions like we have. The other possibility is that you could put the circle inside between the vertices, right, or over here, and just have a situation where the circle doesn't intersect. So it seems like, unless I'm missing something, you could have either 2, 4, or no solutions to this kind of problem. But hey, maybe I missed something graphically just off the cuff. So that's just me speculating at the moment. Anyway, have a good weekend, you guys. I hope this helps you with the mission. We'll talk about any remaining questions you have about it. But I mean, I have to have you turn it in at the start of class. But we will talk about the solution to the mission on Tuesday, if that's what we're going to do. So anyway, see you there, I hope. Thanks. Bye.